just to kind of make things fast, we have a lot to cover. Okay. We have a lot to cover for this section, okay? So we don't want to waste time. Why not? Okay, here we go. So, yesterday, right, we learned about three methods for approximating the area underneath of a curve, all right? And all of those three approximations involve using what kind of shapes? Rectangles. Okay, so we used rectangles, all right? There's a fourth technique that changes the geometric shape of the approximation, and that is known as the trapezoidal rule, okay? So the trapezoidal rule uses trapezoids, all right? So, I know, mathematicians are very creative namers, you know. We like to name things very creatively. So, the trapezoidal rule approximates the area using a certain number of trapezoids, okay? So, remember the area of a trapezoid. So, area of a trapezoid is, 1/2 base 1 plus base 2 times the height. Or sometimes formulated, 1/2 height times base 1 plus base 2. Or sometimes, formulate the whole thing, go up the numerator there and stuff like that too. Okay. By the way, these methods of approximating the area under a curve sometimes are referred to as Riemann sums. Okay, Riemann sums, a name for a mathematician. Okay, whose last name was Riemann. Okay, Riemann sums, methods. Okay, of approximating area under curve. So sometimes we'll refer to it as Riemann sums. Okay. All right. So here we have a nice curve. All right. We'll call this F. All right. And we're going to kind of like draw some trapezoids in here for this specific case. Okay. So we're going to use the trapezoidal rule to approximate the area under the curve of a function. We'll kind of draw a picture example of it here. Now, right, we don't have really numbers, so we're just going to kind of like set it up, but of course not actually get an answer here because, well, we won't have the opportunity. But, so x1 to x2, we have, 1, 2, 3, 4, 5 subintervals here, so we should have 5 trapezoids. All right, and so I'll kind of like draw that in here. Okay, so our first trapezoid, all right, and then there's that first trapezoid, okay, so you can kind of see it here. Maybe I'll just do those solid lines, why not? Okay, so just like that, there's our first trapezoid. So we'll call that T1. Okay, and then same thing here, we'll kind of go up to there and create another trapezoid. Okay, and there's T2. Okay, as you can kind of see, the benefit, right, of using the trapezoids here is that we can kind of, use somewhat of a slope there to indicate, to not overestimate or underestimate so much, right? It's still not perfect, obviously. We still have some values we're missing here, but at least we get, a little bit closer. We can kind of take more into account the increasing and decreasing and how much the function is increasing or decreasing. Okay, let's do the same thing here. And then finally T6. Something like that. Or sorry, T5, I mean. Okay, so there's our 5 trapezoids, okay, that help us to approximate the area under that curve. But of course, how do we come up with the area of these trapezoids, right? So, well, let's take a look here at T1 and just kind of try to understand here what parts are what, right? So, in this particular case, right, the bases of your trapezoid are going to not be the bottom, right? Sometimes we get this idea that the base has to be the bottom of the shape, but it doesn't have to be the bottom of the shape. In the case of a trapezoid, it's always the pair of parallel sides right here. Okay, so what is going to represent this length right here? It's located at the x-coordinate x sub 1, but what is this height? Yeah, the y value, or in this case, we'll put it into f. We'll say f as our function here. And so it's going to be, the trapezoid 1 is going to be 1/2 times the base. We'll come to that in a second here. Or sorry, not times the base, times the height. And then base 1 will be f of x sub 1 plus, and then what's the other base? Well, it's going to be right here, x sub 2. Okay, so f of x sub 2, like that. Okay, what is the height of our trapezoid here? Well, how could we just express it? Or how could we describe it? It would be what distance there? x2 minus x1, exactly right. Okay, so there is the height of the trapezoid. There's base 1. There's base 2. Okay. So if we go back up to here, then question.
What did you say before after the 1/2?
X1, or sorry, x2 minus x1. This is the one you were talking about, right? CT, yeah. Sorry, x2 minus x1. Okay. So yeah, there's that first one. All right. Which means that if you want to go back up here for our purposes, right, the bases, okay, those are going to be y values. Okay? Base 1, base 2, they're actually going to be y values, the height of our curve there. And then the h, that's going to be equal to the width of our subinterval. Okay, so base 1 and base 2 are actually y values. They're the heights, okay, of the left and the right endpoint there. And then height of the trapezoid is actually the width. Okay, so height is width, bases are the heights, okay, because of the way our trapezoid's oriented here, okay, the way our trapezoid's oriented. So let's do a few more here. So trapezoid 2 then, it'll be 1/2. What's going to be our width here for the second trapezoid? x3 minus x2, right? Okay, this minus this, times f of, okay, what's our base for trapezoid 2? X sub 2 plus f of x sub 3 there, right? Okay. You'll see that x sub 2, the f of x sub 2 is going to be used twice. Once as the right side of trapezoid 1, but trapezoid 2 is going to use that f of x sub 2 as the left side of trapezoid 2. Okay? So trapezoid 1 and 2 both use f of x sub 2 for their bases. But then x sub 1, the very first side there, only get used once. So this will be used twice, 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 and then of course our very left and rightmost sides will only be used once. Okay, so I'll just put like a dot, 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 and we'll do like the t sub 5, okay, which is then 1/2 x6 minus x5 times f of x6 plus f of x5, or f of x5 plus x6, whatever there. Okay, and of course then to come up with that, right, we would add up those sums, okay, whatever they would be, and we would get our trapezoidal approximation. And we add those up, right? Whatever that would be. That would be our answer. Okay? Additionally, right, we want to kind of take a look and see here and identify when we can expect to be overestimating and when we can expect to be underestimating. So if we look back up at our shape here, all right, what kind of behavior seems to create an underestimate and what kind of behavior seems to create an overestimate in our curve here? What does it look like, Lee?
Concave down looks like an overestimate, and then concave up looks like an underestimate.
Close. So concave down, yes, but so like for example, here our curve is concave down, right? Is that trapezoid overestimating or underestimating the actual area underneath the curve there? Underestimating. So yeah, so concave down in this case is an underestimate. Concave up will be an overestimate, okay? Which is reversed, right? Reversed from our midpoint, okay? So for trapezoidal rule, okay, overestimate for concave up. an underestimate for concave down. Okay. Overestimate for concave up, underestimate for concave down. This is a little bit easier to see if you just draw a picture, right? So I don't even know if this is something you necessarily need to memorize. If you just, can draw a picture, be like, okay, well, here's like a concave down. If I draw a trapezoidal rule here, like just with an interval of 2, I can kind of see, okay, well, it's clearly going to be, an underestimate. My trapezoids are going to be an underestimate. Where if I draw, a concave up kind of thing, if I draw 2 trapezoids here, it'll be like, okay, well, there's very clearly an overestimate there. So you can also kind of just draw a picture to help convince yourself, for the concavity's sake, what it's going to be. All right. Let's move on here. So let's actually do one, right? So let's do the sine of x, okay? And so we're going to use the trapezoidal rule to approximate the area under the curve. Yeah. N equals 4. What do you think it means? Number of trapezoids. Exactly right. Yep. Exactly right. So, and that's a typical, way that it's described. I know we haven't talked about that yet, but exactly right. Very good. So, let's draw a picture of the sine of x from 0 to pi first. Okay. All right. And so let's see, I'll do like the halfway point here, pi over 2 as well. So, sine of 0 is 0. Okay. Sine of pi over 2, 1. And sine of pi, 0. Okay, so our curve's going to look something like that. Right, for the sine there. Okay, so there's sine of x. Okay, but of course we want 4 subintervals. So we want to go a total distance from 0 to pi there. So the total distance from 0 to pi, what's that total distance? What's the total length from 0 to pi? Yeah, pi, right? The full interval, the entire interval is from 0 to pi. So an easy way to calculate that, right, is just to do pi, take away 0. But we want to divide that into how many subintervals? 4. So we're going to take the full length, pi minus 0 there, divide it by 4 subintervals, and so we end up with pi over 4 is the width of our subinterval. Okay? It's the width of our subinterval, which means then that if we start at 0, what will be the end point of our first subinterval? Pi over 4, right? We're going to go in pi over 4 to pi over 4, and then another pi over 4 gets us to 2 pi over 4, or pi over 2, and then another pi over 4 gets us to 3 pi over 4, and then we get to pi. Okay, so there are our 4 subintervals. And if we want, we can then graph kind of the trapezoids here. So again, there's our first trapezoid. Okay, it's really actually a triangle, but anyway. All right, and then there's our second trapezoid here. Okay, and then our third trapezoid. And then our fourth trapezoid. And again, it's more of a triangle than it is a trapezoid. Okay, so T1, T2, T3, T4. Okay, so let's see here. So we'll go ahead and start finding the areas of these trapezoids, right? So T1, T2, T3, T4. Okay, so going back to our area formula for the trapezoid, we're always going to have that 1/2 times the height. Okay, so we're going to have all these 1/2s in front. Okay, what are the heights for all these trapezoids going to be? Pi over 4, right? Remember, the height is the width of the subinterval here. So it'll be times pi over 4, pi over 4, pi over 4, pi over 4. Okay. And then for this first trapezoid, okay, what are our 2 bases? We want to, so I guess we're the left endpoint and the right endpoint, right? We have 0 and pi over 4. So the bases are their heights. So we're going to say f of 0 plus f of pi over 4. Okay? And then we'll say f of, for the next trapezoid, we're going to do f of what? Pi over 4 plus f of pi over 2. Okay, and then we'll do f of pi over 2 plus f of 3 pi over 4, and then f of 3 pi over 4 plus f of pi. Like that. Okay. Now, excuse me, with this one, since this is trig, we can evaluate these, kind of mentally, right? We can do this, and we could just like write the sum as our solution, right? So is a calculator necessary for this one? No, not really. Okay, we can just kind of like write the sum out as our solution here. But why not just kind of get some answers here with this? So let's see, 0.5 times pi over 4. Let's actually just do it here. Okay. So then let's see here. So now I'll store that as x, and then we'll do let me see, how do I guess I'll just say that times 0 plus root 2 or 2. Okay, so I get this to be about 0.278. And let's see here. Plus 1. I get this to be about 0.670. And let's see here, another root 2 over 2. Oh yeah, that makes sense because of symmetry there. A dewey. Okay. So you can kind of take advantage of the symmetry here too, and actually realize we're going to get, kind of like the same values there. And so then if we add these all up, okay, we get about 1.896. Okay. And we expect this area to be a over or under approximation? Under approximation. You can see it in the picture, right? You can see in the picture all these trapezoids are just kind of slightly under that curve, but it's specifically an underestimate because of what behavior? Underestimate because f is concave down on the interval. Okay, if we wanted to be sure that it was concave down on the interval, what could we do? I mean, obviously, we can kind of look at it and see it's concave down, right? But you can't really say it looks like a frown, so therefore it's concave down. How can we actually like justify using calculus that this function is in fact concave down from 0 to pi? What could we do? Okay, take the derivative, so we would get f prime. Is that all we need to do? We really need the second derivative, right? So you can look at the second derivative and show that the second derivative will be, what? Not decreasing, negative for concave down, okay? So we want to show that the second derivative here, if we wanted to, like give even more kind of like, support or justification here, we could say, take the actual second derivative of this, show that it is negative from 0 to pi. The second derivative will be negative from 0 to pi, okay? Or that the first derivative is decreasing. Another idea too. Okay. All right. Anyway, moving on. All right. So let's try this one here. All right. So we're going to approximate the area between the x-axis and the curve here, x squared minus 2x, from 1 to 3. Using 5 trapezoids. Okay. So again, let's figure out what the width of our subinterval is going to be here. Okay. So again, to figure out the width of that subinterval, what's the full distance we want to travel? 2, right? We're going from 1 to 3. Again, we can figure that out by just doing 3, take away 1. But we want to divide that full distance into 5 equal subintervals, so we'll divide it by 5. Okay? So, some way this thing is formulated is you take b minus a over n. So the general formula for the width of a subinterval is b minus a. your right endpoint of your full interval minus left endpoint, so b minus a, and then divided by n, the number of subintervals. Okay, so that's kind of a general formula there, but the basic idea is what we just talked about. And so 2/5, right? 2/5 is going to be our width of a subinterval there. Okay, or in other words, 0.4. Okay. So I find it helpful sometimes when I'm going to like do these problems, not so much to draw the graph, but just to maybe like draw out my subintervals. So I know if I start at 1, okay, what will be my next endpoint? If my subinterval width is 0.4, if I start at 1, what's the next endpoint for my subinterval? 1.4. And then the following one, 1.8, and then 2.2, and then 2.6, and then finally 3, okay? So it's just helpful for me to have that drawn out to figure out exactly, where, so on and so forth, okay? It's just helpful to have that drawn out so we can know where our subintervals are and stuff like that, okay? So for that first trapezoid, which, we're going to have right here, so here's T1, T2 will be right there, T3, T4, and then T5, okay? However those are going to be drawn. Okay, so T1 will be 1/2. Okay, what's the height of our trapezoid? 0.4, 2/5, yep. And that's going to be true for all of these, so we can just put the 1/2 times 0.4, 1/2 times 0.4, 1/2 times 0.4, 1/2 times 0.4. Again, when I say the height of the trapezoid, remember that's really the width of our subinterval. The width of our subinterval. Okay. And then all those get multiplied. Okay. So for our first trapezoid here, it's going to be f of what plus f of what? F of 1. 1.4, exactly right. Okay, the two bases there. And then for the next trapezoid 2, it's going to be 1.4 plus f of 1.8, and then so on and so forth. You guys can do the rest. I won't make us, kind of go through the whole thing there. Okay. So now at this point, right, it's just a mess with the calculator, okay? So you can kind of like, in fact, I'll probably get some like nasty decimals here. Well, okay. So I'll go ahead and simplify some of this, right? We'll do 1/2 times the 0.4, so you get like 0.2. All those are going to be 0.2s in front there. Because 1/2 times 0.4 is 0.2. And then we'll just figure this out with the calculator here. So, in fact, maybe I'll just go ahead and just do the math rather than... Okay, so... Yes.
How are you putting in a calculator? Are you finding f of 1 and then f of 1.4 and then adding it in your head?
Yeah, you can do it that way. Or you can just use a calculator then to add them up and stuff like that too, yeah. There are easier ways. Well, you can like kind of be a little tricky with how your calculator does it and stuff like that.
There's no way to put in
Nothing that I can think of off the top of my head. Let me check here something real quick. Hmm. Oh, that's why. Dur, dur, dur. Okay. Interesting. I think I might have I might have found something that could be helpful here. Function y1 of x plus
No way built into the calculator. I feel like the sum of the
yes, I think so. Hang on though, real quick.
Yeah.
Negative 0.368.
Game's that I'm trying to maintain serious, and game's just like later, buddy.
It happened. Honestly, both options are very
Don't feel too bad. I'm the only tall one. Wait, what?
Yeah.
No.
See you there, Brad.
They couldn't go Yeah.
Are you actually in it?
Yeah, it's gonna be me,
You're so good at volleyball.
Michael Gula,
Wait, you guys are playing?
yeah, it's on the winner's
They like don't play it right?
Y. McCoy, Ross, Jeremy
No,
Brown.
I don't think
So I'm
that's
really
happening.
the only tall
You're
person.
like, okay, but it's fine. No, I don't graduate.
At least 2 years ago, so Charlotte, Rachel played.
So funny, one
Honestly, we would have had a team. I would play.
Which part for the lightest kid in the room?
Yeah.
That was like wrestling.
Yeah, it's all there's a,
So, okay.
Mr. Woodland.
Yep.
Are you playing in the volleyball game today?
Say what?
Are you playing in the volleyball game today?
I am.
Apple's making it on there.
Probably.
It's cool too. It's
What's that?
Yeah, Miss
what's your
Cole, Goff, me, SoCash, and I think Graziano.
as long as Trigger is in. Trigger's like a monster. You literally just stand at the net and just go like this. And you'll be alright.
All right. What did you guys get for the area of this first trapezoid?
Negative 0.36.
Negative 0.368. Okay, but that is the area, right?
Yeah.
Okay, so
Yeah, that was my question. How can an area be negative?
it has to do with its location, which is below the x-axis. So yeah, what's the question?
How do you get that?
How do you get that? So it's the calculator. But now I think I found a way that's a little bit helpful here. So let me show you something, okay? So what I did, okay, was because we are going to be using this, x squared minus 2x with like repeated calculations, all right, is I put the x squared minus 2x into my y1. Okay, put the x squared minus 2x into y1. And then in y2, what I did is I did 0.5 times 0.4, which is going to be what we're going to multiply in front here, and then times, guys, it's important, look up here, okay, times y1, okay, which is, what is y1? It's the function. And I'm putting y1 parentheses x, and what the calculator reads that as is x evaluated in, whatever your x value is, it's going to evaluate that in the y1, okay, and then plus y1 times, I did x plus 0.4, because that's what our subinterval is. We have to add 0.4 to whatever that x value is. And then I close the parenthesis. And so then when I go to my table, if I type in 1, which is like the left endpoint of my first trapezoid there, it gives me that sum. If I type in 1.4, did you guys get negative 0.24 for your second trapezoid? Yep. Okay. So then we can just type in those left endpoints, 1.8, and we get 0.016, and 2.2, and we get 0.4, and 2.6, and we get 0.912. Okay, so that does work. Pretty crazy. Like what I typed in? Yes, sure. So I typed in the function here, okay, and then because I want to use that function twice, I went down into y2 and typed in what like my trapezoid area formula would be. So 0.5 times 0.4, 0.5 for the 1/2 right out front, 0.4 for the subinterval, and then I did y1 of x. So in other words, we're like going to use just like y1 applied to x, whatever that x value is, we're going to pick, in our table, of course. And then y1 of x plus 0.4, because we have two f's that we're evaluating here, both the left endpoint and then 1.4 from that, or sorry, not 1.4, 0.4 from that, the right endpoint kind of thing. Okay?
Where's the Y1 button?
The Y1 button, great question. It is in the vars. So if you press vars and you arrow over to y vars and then function, you can see all your different y's there. You just hit enter to use that. Okay? And so that allows you then to set up a kind of like a way to save yourself some time there as long as you set it up correctly. All right? And then you go to your table and you just type in your left endpoints here. So again, I went through and did my left endpoints. 1, 1.4, 1.8, 2.2, 2.6. The y1 information you ignore, okay, because that's just, f of that. But here, y2, that's your trapezoid areas. Okay? Pretty nice, pretty handy for those repeated calculations, right? Pretty handy for those repeated calculations. Okay? And so then we should be able to add those up using just what we have now. And we end up with, oops, I think I made an error in my, should be 0.912. And we get about 0.72, which is the answer there when we add those up. Okay, is the area. Okay. And so I understand what you guys are asking, though, about the negative. I'm glad you're asking that question. Okay, depending on the context of the situation, sometimes we will just want to make these positive, but sometimes, depending on the context of the situation, we want to keep it negative, okay? Yeah, and so for these situations, we're going to keep it negative. We're going to add this up, okay? But for other situations, you're right. The area should never be negative, but because of what this is going to lead into, it will be negative for the kind of problems that we'll be working with and stuff like that, okay? So for the time being, we'll leave them as negative, even though we are talking about areas of trapezoids and things. Okay, so you should get 0.72 there for your final answer. All right, so unfortunately, the next problem here, we're not going to be able to practice that, what I just showed you. But anyway, so example 3. Okay, now we're going to finally here move on after that nice long pause there. All right, we're going to approximate the area between the x-axis and f of x found below. So here's f of x from -1 to 5 using 3 trapezoids. Okay, so what is the width of our subintervals here? The width is 2, yes, okay, because the total distance we're trying to span here is 5 minus -1, and then we're going to divide that into 3 subintervals. So 5 minus -1 is really 6 over 3, which is then 2. So our width of our subintervals there is 2. Okay, so let's go ahead, because we can here. Let's draw in our trapezoids. Again, we're starting at -1, so not at -2. We're starting at -1, and we're going to 5. Okay, so let's see here, from -1 to 1, okay, what kind of shape are we actually going to create here? It's actually a rectangle, okay? So yes, we're going to use the trapezoid area formula, but it'll still be formula for a rectangle there. Okay, and then from 1 to 3, okay, there's that. And then from 3 to 5, there's that. Okay. This function is most likely what kind of function? It's probably piecewise, right? If you just look, we have like a parabola, we have a constant, and we have linear, so it's most likely piecewise here, okay? So this is how you could potentially, do this using, a piecewise function and stuff like that. Anyway, let's go about our 3 trapezoids here. So T1, T2, and T3. Okay, 1/2 times, times 2. 1/2 times 2, 1/2 times 2 for all those. Okay, and that's going to be f of -1 plus f of 1, f of 1 plus f of 3, and then f of 3 plus f of 5. Okay. So we're going to have, 1/2 times 2 is just going to be 1. Okay. And so then f of -1, what is that value? 2, right? Just look at the graph. Y value is 2. F of 1, also 2. Okay. F of 1, 2. F of 3, 5. Okay. F of 5 again, or sorry, F of 3 again, 5, plus, and then F of 5, 1. Okay. So we get 4, 7, and 6. So we'll add those all up, and we get 217. Okay. And again, that's our approximation there. Okay, that's our approximation. So there's an example of a situation where we don't need a calculator, right? Really, a calculator, I guess you could use it to help you with the arithmetic and stuff, but not necessary. Okay. Also keep in mind, right, that at this point, okay, so there's no need to actually find this sum if it's a free response question. You may absolutely leave it in, this format, circle it, and say that's my answer. Remember, you do not need to simplify arithmetic in a free response question. Okay. In fact, I would caution against it in a free response question because you might make an arithmetic error, and then that would cost you a point. Whereas you can just leave it like that. So either one of those are acceptable. All right, let's move on here. Okay, so in example 4, okay, now of course we've got a table. All right, so it might be helpful here. Letter A says to draw a graph that could represent the car's velocity during the hour. All right, so this table represents readings from a car's speedometer at 10-minute intervals during a 1-hour period. Okay, so given the table, T is the amount of hours or fraction hours, and then V is the speed in miles per hour, even though we are using a V to record it, but it's speed. So all right, so we'll see. There's T, there's V, and let's see. We're going from 0. So there's 0 60ths. We'll say, Mr. Witt, 10 60ths, and there's 0 60ths right there. Okay, and so then 20 60ths. So let's just graph this thing, get an idea kind of like what it looks like. Okay, it looks like we have to go all the way up to 60 here, so I don't know, go like 10, 20, 30, 40, 50, 60. Okay. Just make ourselves a graph. Again, the graph is helpful because it'll kind of help us to figure out, what we're looking at, what we're considering here and stuff. All right, so at 0, okay, at time 0, we are at 26 miles per hour. So when we start this process, at time 0, we're at 26. I'm going to roughly, put that right there, and so that's the point 0, 26. I'll say. I'm just going to label the point for ease of, kind of like looking at it and stuff. And so let's do 10 60ths, which is 40. It's a nice, easy. Okay, and then 20 60ths, we're at 55. Let's see, 30, 60, we're down to 10. And then 40, 60, yes, we are all the way up to 60. Some sort of crazy traffic. Okay, and then 50, 60, yes, we're at 32. Okay, and then finally at 60, 60th, or 1 hour, we're at 45. Okay, and so how does this look? Well, we can kind of make like just a nice... Now, the key word here is that this could represent the car's velocity during the hour, right? Do we know anything about what happens between minute 0 and minute 10 here? No. And so the car could speed up to 100 miles per hour and then back to 0 miles per hour and then get to the 40, okay? So we are saying it could represent this, but it doesn't have to. Okay, so you want to be very careful, right? The only things we know for sure is that the car is getting from here to here to here to here to here to here to here, and has to at every speed in between there to get from where it goes to where it is, right? By the intermediate value theorem, right? But beyond that, we don't know. It could, the speed of the car could go all the way up to 100 miles per hour and back down to 0, like I said before, it gets that first subinterval point. So just be careful with that, okay? We don't want to assume that this is what the car's speed looks like, okay? But it could be. Okay. So letter B then says, find the area under the curve after 40 minutes of driving using the right Riemann sum, or in other words, the right endpoint approximation with 4 equal intervals, okay? And then what is the meaning of this area underneath the graph, okay? So why don't you guys go ahead and set that up. This is a right endpoint approximation, 4 equal subintervals after the first 40 minutes of driving. Maybe I'll help you get started on the first rectangle, right? So for rectangle 1, okay, what is the width of our subinterval going to be here? If we're doing 4 intervals over 40 minutes, how long is each interval? 10 minutes. And we're doing the first 40 minutes, okay? Actually, it doesn't say the first 40 minutes here, but I think we would have to assume that. Otherwise, it could be 40 minutes for a different part. So we'll say the first 40 minutes. So our first subinterval there is going to be a width of 10 times, and then which endpoint is going to determine the height here? Are we going to do f of 0 60ths or f of 10 60ths? 10 60ths because it is the right endpoint, the right Riemann sum. So it'll be f of 10 60ths, which is 10 times 40, or 400, right? So you guys go ahead and do the rest. R2, R3, R4, and I'll do them simultaneously. Okay. So this number that we find has more meaning than just an area under a curve. Why? Because we are in a context here. The context is velocity, right, speed, and miles per hour and stuff like that. So anyone want to take a stab here at what that 1,650 means in the context? Yeah.
Which area has been covered after 40 minutes?
Okay, so the area that's been covered after 40 minutes. So that's true. It is the area under the curve here. But in the context of the car, I like the fact that you said after 40 minutes. That's good. But I need more specificity, I guess, about what's happening with the car. This is the what?
Like maybe how many miles per hour, or how many miles it's traveling?
Oh my goodness. You know what I'm thinking about right now? Yeah. 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 So the problem is right now, right, we changed our units. So the problem right now, what we're looking at, is these tens are all a quantity of what? What are their units? Okay, they are minutes, right. Okay, so these are 10 minutes, but then we're multiplying by f of something, but what are these function values?
Per hour.
They are in miles per hour. Okay, so if we're doing minutes times miles per hour, not the greatest thing here. So instead of saying 10 minutes, okay, we probably should have done 1/6 of an hour. Okay, so instead of 10 times 40, let's make those 1/6. I know, Mr. Widd, what a jerk.
Carter got the right answer.
Okay.
Wow. Thanks for telling us, Carter.
Okay. So we'll get 6.6 repeating there, okay? We'll get 9.16 repeating there. Okay, 1.6 repeating here. And then, so 1/6 times 60, that's an easy one, 10. Okay, so 10.0 repeating, sure, yeah. So we get 27.5 when we add those all up. Okay. So is everyone clear about why we had to make that 1/6 instead of 10 there? Right, we're mixing our units, okay? So we want to make sure that our units, kind of go together. So that was in minutes, now that's in hours, okay? Which then combines correctly with our miles per hour there. Okay. So if we're taking a quantity of hours, multiplying it by miles per hour, so we have hour times miles per hour, what happens to those hours? They're going to cancel. Because it's hour over hour, they cancel. And so what are these quantities right here? A number of what? These are all miles. So when we add these up, we can say after the first 40 minutes, the car, what? Drove approximately 27.5 miles. After the first 40 minutes. Okay, 27.5 miles approximately driven by the car after the first 40 miles. Minutes. 40 minutes. Can't read my own handwriting there. Okay? Okay. So here's another one for us to try, okay? So we're going to find the area under the curve after the 40 minutes of driving using a left Riemann sum. Okay? Left Riemann sum here. How we doing on time? Crikey. Okay, so go ahead, set that up, solve it. Okay. Say again? Nope, you don't need to draw it. Nope. Just set it up if you want to. Now we'll be careful with our times though, right? So we'll say 1/6, 1/6, 1/6, 1/6 there. Okay. Oops. Oh, I guess I need to do that. All right. when it comes to determining, if possible, if this is an over or underestimate, keep in mind for left endpoint and right endpoint, or in other words, left Riemann or right Riemann sums, what behavior do we look at? Whether it is concave over concave down is not for left and right endpoint. That's for midpoint or trapezoidal rule. Increasing and decreasing, right. So with this scenario, is it an over, is it an under, or is it not possible? It is not possible, okay? Because from 0 to 40 minutes, what kind of behavior do we see? Yeah, we see both increasing and decreasing. Even if we saw from 0 to 10 here, we do want to be kind of careful. We don't know necessarily what's happening in the intervals between. So even from 0 to 10, where it's very clearly we're increasing in general overall, we want to be careful though, because we don't know what's happening in between. That approximation still could be an over or underestimate, okay? Because we don't know what's going on in the meantime, in the in-between intervals there. So that's why we want to be careful.
So if something like that was asked for us to do, over or under, and it said about, would we, in this problem, when it says over or under, would we say you don't have enough information to decide?
I would say, yeah, you don't know. Yes, I would say you just don't have enough information about what's going on in the intervals, okay? The function, I should say. The function increases and decreases. In this interval. Okay, it's for our justification there. Okay, so it's not possible to determine. Okay? All right, midpoint. Believe it or not, we can do a midpoint Riemann sum here with 3 equal intervals. So if we're going to do for the whole 60 minutes, so if we're going to do 3 equal subintervals over the whole 60 minutes, how wide are our subintervals going to be? So 60 minutes divided by 3 equals 20 minutes, okay, which is going to be, 2/6 or 1/3 of an hour, okay, 1/3 of an hour. So for our, midpoint, our first interval is going to be 2/6 of an hour or 1/3 times, so for the first 20 minutes, what is the height of the midpoint? So there's rectangle 1 for the midpoint. What's the height of the midpoint of our rectangle 1? 40. Okay, 40. Exactly right. That's the midpoint there. Okay, right? There's left endpoint, right endpoint, but the midpoint's 10, so it's at 40. So height of 40. Okay. The second rectangle here is from, let's see, now what am I doing? From 0 to 20. Oh, yes, here we go. Second rectangle will be from 20. Maybe I should have done all right, whatever. 20 to 40 here, okay? So there's R2, okay? What's the midpoint from the 20 to 40? 10. The height will be 10, so 1/3 times 10. And then from the 40 to the 60 there, for our third rectangle, the midpoint, what's the midpoint of that rectangle, of height? 32. Okay, so maybe I should have done it this way. There's rectangle 2 right there. Like that. Okay, and so then we can add those up, or multiply those. So 13.3, 3.3, 10.6 repeating. Okay. There we go. So 27.3 repeating. Okay, 27.3 repeating there. Okay, again, that's in miles. Okay. the interest of time, we'll do this next one here, but we'll just do it after the first 40 minutes, and we'll just use 4 equal intervals here, okay? So we'll use the trapezoidal rule here real quick too. Okay, so trapezoid 1, trapezoid 2, trapezoid 3, trapezoid 4. Okay, we're all going to have the 1/2s. Okay. The widths of our subintervals, if we're going 40 minutes and 4 subintervals, it'll be 10 minutes each, which is 1/6 of an hour. So we're back to the 1/6 width there. Okay. And again, for that first subinterval, from 0 to 10, it's going to be 26 plus 40, right? Left endpoint plus right endpoint. And then for the next interval, it'll be 40 to 55. And then 55 plus 10. Okay, because 55 plus 10. So we had 26 to 40, 40 to 55, 55 to 10, and then finally 10 and 60. Okay, for those left and right endpoints each. Okay, equals, and then you guys get the idea from there. You can calculate from there, right? You're going to add them up and get some number of miles. Okay, whoops, there we go. All right. Questions on letter E? Are we all okay with that? Okay, you should, if you get that, you should get approximately 24.667 miles there when you do that. Okay? All right, moving on. I want to get to this last one here. Okay. So, number 5, the table below shows the rate at which water is coming out of a faucet in milliliters per second over different periods of time. T is in seconds, and R is the rate of volume of water in milliliters per second. Okay, so this is nice because our time is in seconds, our rate is also in seconds, so we don't have to worry about like converting, from minutes to seconds or minutes to hours or anything like that. We're time is seconds, milliliters per second for the rate, so that's good. We're going to skip the graph for now, again, just to save on time. All right, we're going to jump down to letter B here. So we're going to letter B, approximate the area under the curve after 10 seconds, so that's from 0 to 10 there, using the left Riemann sum with 4 subintervals, okay? So, if we're going from 0 to 10 in 4 subintervals, what's the width of each subinterval going to be? 2.5, okay? But if we go up to our graph here, do we have 2.5? No, okay? But this is a scenario where we're going to use uneven interval widths. Okay, so what we're going to do is we're going to give the best approximation we can, okay, but just not use even subinterval widths. Okay, so you can see here that from here to here, that's going to be rectangle 1, and then from here to here, that will be rectangle 2, from here to here, that will be rectangle 3, and then from here to here, that will create rectangle 4. So we have 4 intervals here, from 0 to 3, 3 to 4, 4 to 8, and 8 to 10. But we ought to be careful because they're going to be different widths, okay? So for example, for rectangle 1, what's the width of rectangle 1 going to be? 3. Okay, so the width is 3. And if we're using the left endpoint approximation, right, the left endpoint, what's the height of it going to be, 8 or 12? 8, right? Okay. R sub 2. So for R sub 2, we're going from 3 to 4. So what's the width of that rectangle going to be? 1. And then which endpoint are we going to use, the 12 or the 15? 12, right, and then so on and so forth, okay? The width of rectangle 3 is going to be 4, and then its height will be 15, and then the width of rectangle 4 is going to be 2, and its height will be 11. Okay, so it's 3 times 8. Okay, so 24, 1 times 12, 12, 4 times 15, 60, and then 2 times 11, 22. So, 118. Okay. Now, what would the units for this 118 be? 118 what? Well, it's in a context, right? The 3, the 1, the 4, and the 2, what were those units? Seconds, right? Time, so seconds in this case. And then the 8, the 12, the 15, and 11, those were what? milliliters per second. So what happens to the seconds? They cancel, and we're left with 118 what? Milliliters. So what would be the meaning then? The amount of water that has what? That has come out of the faucet for the first, 10 seconds, okay? So 118 milliliters of water, I should say approximately. Oh, I'm going to run out of space. Okay. Approximately 118 milliliters of water came out of the faucet in the first 10 seconds. Okay, that's the meaning there. Questions on any of that? Okay, so the next thing is a right Riemann sum, but I do want to talk about the trapezoidal rule here real quick. We'll skip the right Riemann sum. I think you get the idea of that, but let's use the trapezoidal rule for this one real quick. So we're going to have 4 trapezoids. Okay, against 1/2 times the base. Okay, so again, trapezoid 1 will be from here to here, trapezoid 2, there to there, trapezoid 3, and then trapezoid 4. Okay? Sorry, yes, I need to zoom out maybe if I can do it that way. Okay? So, that first trapezoid, what will its height be? 3, right? The width of the subinterval, times the bases, the 2 bases. So it's going to be 8 plus 12. Okay? And then for the second trapezoid, width is 1. And then 12 plus 15. Okay? And then for the third trapezoid, 4 is the height. And then 15 and 11. 15 plus 11. Right? And then 8 and 10 times 2. And it's going to be 11 plus 5. Okay? And of course, then we can add those all up. And I think I have an answer for that one. It should be about 111.5 milliliters. There. Okay. Whoops, I'm off the screen. There we go. Okay. So then those are your heights right there. One thing I want to mention, okay, one last thing I want to mention here, okay, in the book, for your homework tonight and for the weekend thus also, right, or for the long break here, you're going to see problems like this. Okay, they're going to ask you to approximate using, trapezoids or something like that. And so what this is saying is approximate the area under the curve of x squared from 0 to 4 for the interval 0 to 4 in 4 trapezoids, right? That's the idea. That's what that's asking you to do, okay, for your homework. So just as you understand that, okay? So this is, that's your interval from 0 to 4. You're going to approximate the area under this curve using n equals 4, okay? That's what that's asking, okay? Just approximate using trapezoids. It's just, this is how we're going to bring together what we're doing right now with integration. Okay. So, okay. Set requests for today. All right. Yes.
Did you really not get my homework this one, Mark?
I did not. So, Emma, I got you guys. Anybody else for set? So, Mario, I'll give you credit in now, but I would say in the future, make sure that you give it to me because, I don't know.
I was sat beside you because I thought you were going to come back.
Well, and I think you're wrong on your time because Ashley was in here at 2:30, whether I was or not. So you wouldn't have had to shove it on the door. So I don't know what time it was, but
I don't know. I just know that the room was completely black.
right. So that was probably like after 2:45 then or something.